after working in Princeton with Jim Stone on various instabilities, magnetothermal instability in particular, which I think we'll hear a little bit about today, he got a Chandler Fellowship and moved to UC Berkeley, where he's been a postdoc for the last several years. He's done a lot of work on galaxy clusters, and today he's going to tell us a little bit about that.
Thank you. I appreciate the invitation. So it's nice to be visiting in beautiful fall weather. I missed the seasons in California a little bit. So I'm going to tell you about galaxy clusters and sort of two different topics in galaxy clusters. And feel free to interrupt it and let people understand and follow along and step forward. And I'd really like to highlight the work of one of my students, Mike McCoy, who's a grad student working with me, who's contributed significantly to the projects I'm going to talk about today. So first of all, we start with the obligatory pretty picture. So this is the Perseus galaxy cluster, a nearby, quite large galaxy cluster, and the central galaxy, which is NGC 1275. And this is a picture from a nice Nature article by Andy Fabian. And what you can see, I don't know if you can't see it very well on the screen, is these beautiful H-alpha filaments, which are going, and this is superimposed on the X-ray image. Yeah, that's a little bit better. And what these filaments are these just incredibly thin filaments that can be 10 to 20 kiloparsecs long, and they're so thin that they're below Hubble's resolution, even at the distance of Perseus. So it's an upper limit of tens of parsecs. So there's all these very interesting, and these are made of atomic and molecular glass. So there's a lot of really interesting physics going on in the middle of the hot intercluster medium, and this is one of the things I'm going to talk about today. So let me outline my talk. I'm going to tell you a little bit about galaxy clusters, for those of you that aren't familiar with them. And then the title of my talk, because we're going to use a catchy title, is Galaxy Clusters from Inside to Out. So I'm going to spend some time talking about the inside of galaxy clusters. And namely, what I'm going to try to address here is where do these filaments come from? How does thermal instability work in this multi-phase medium? I'm going to talk about some of the theory and some of the observations and numerical simulations, and I'm going to try and explain this in the context of how this can self-regulate the state of the galaxy cluster, as well as feeding the supermassive black hole at the center. And then I'm going to move to the outside of the galaxy cluster and talk about something quite different. I'm going to talk about this instability that Shane mentioned, the magnetothermal instability, and how it can provide some reasonably large turbulent pressure support in the outskirts of galaxy clusters, and what that means for surveys of the Sunyaev Zel'dovich effect, which you've probably heard a lot from some of the local people here. All right, so what are galaxy clusters? Well, they're the largest gravitationally bound objects, 10 to the 14, 10 to the 15 solar masses, virial radii of 1 to 2 megaparsecs, and they're hot. They're filled with a hot dilute intercluster medium, which actually makes up the majority of the baryonic matter in the plasma. Most of it's dark matter, which we can't see. But we often like to know the total mass of these objects because they're on the exponential tail of the mass function. And because of this, cosmological parameters like sigma 8 and mega matter are exponentially sensitive to galaxy clusters. So they have the potential, the keyword here is potential, to be a very useful cosmological probe if you can correctly infer the total mass of the cluster from the sort of 13% of matter that you can see. They're also neat in terms of being cosmological laboratories, in that because they're the biggest objects in the universe, they have the biggest galaxies inside of them, the large brightest cluster galaxies that reside at the center, which in turn have the biggest black holes that sit in the middle, 10 to the 9, and there's even a 10 to the 10 solar mass black hole confirmed recently at the center of one of these. And these are just some images of them. So we study the hot intercluster medium through the X-ray emission of the multi-KeV gas. You can also study them using their optical light. And finally, these central black holes often produce some very spectacular relativistic jets that inflate cavities in the intercluster medium. One of the things I'm going to focus on today, which is more than half of the galaxy clusters that we see in the universe, are what we call cool core clusters. And so if I plot at sort of a non-dimensionalized temperature profile versus the virial radius, you can see that in the inner 10% of the virial radius, there's a sharp decline in temperature profile towards the inside. And this has been an interesting puzzle because if you ask what the cooling time is in the central region of this galaxy cluster, it's often significantly shorter than the Hubble time. There's as short as hundreds of megayears around a few kiloparsecs. And so, absent a heat source, there would be this expectation that you would have very large rates of star formation, very large amounts of gas cooling out of the hot intercluster medium. This is what was known as the classical cooling flow, and star formation rates of thousands of solar masses per year. And this is just simply not observed. Most of this gas actually manages to stay pretty hot, somewhere around a third of the real temperature. So this means there must be some sort of a heat source that's balancing the radiative cooling. And not only does it need to balance the radiative cooling, but it needs to do it in some sort of volume average way. And so one possible way is you see these jets from the central black hole. This could be doing some sort of mechanical work, or driving waves or shocks that heats the surrounding medium. Or you could have conduction from the relatively hot outskirts of the cluster. So within these galaxy clusters, there are observations of multiphase structures. So I just want to take you through the observations a little bit before I get to the theory and the simulations. So what do the observations tell us? So first of all, we know that there's not a classical cooling flow. The observed cooling rates as measured by Exon and Newton line diagnostics are hundreds of times lower than what would be the classical cooling flow rates. So this means that heating and cooling are, in average, globally imbalanced in these cluster cores. The second thing is there's actually lots of evidence that there is cold gas, however. And so this is seen in the H-alpha, it's seen in the CO and other molecular lines. You even see pH is sometimes in the very center of these. And there's a whole host of papers here by a number of people that have been measuring cold gas in the center of the clusters. And what does this mean? Well, this means that heating and cooling are not always in balance. There's times when they're, in fact, out of balance and material is able to cool. And so what do we know? We have a really good idea what the cooling rate is. It's just Bremsstrahlung lines. But in terms of a heating rate, as a function of density and temperature and position in the cluster, we have no idea. So the upshot of this is that clusters are globally thermally stable, but can be locally thermally unstable. And this difference between global and local stability is something I'll come back to during the course of this talk. In terms of more concrete observations, one of the ways that observers like to parameterize statistics about galaxy clusters is through their central entropy. And cluster observers define this in sort of a funny way. It's the density, or it's the temperature divided by the density to the 2/3. So real entropy has a logarithm of Boltzmann's constant times this. But the central entropy correlates quite nicely with the H-alpha emission in the central, which represents star formation. Also the radio emission from the jets. And you can see this right here, where there's below some sort of critical threshold, which is about 30 keV centimeters squared. There's quite a bit of H-alpha luminosity, whereas above that threshold, there's actually very little detected. These are all upper limits on this side. And these are sort of your classical cool core clusters. And the other thing we see is that we see energy from feedback. So these large buoyant cavities that are inflated. And it's a tricky game to estimate just how much work they're doing to heat their surroundings. But in a horseshoes and hand grenade sense, the heating rate from these buoyant bubbles is probably largely balancing the cooling rate inside the galaxy clusters. So there's sort of two key questions. Where does the cool gas come from? And what is the role of cool gas in the feedback cycle? Is this what's feeding the central black hole, which is then driving the feedback? Okay, so let me move a little bit more to a slide with some theory. So I was told that I could use math here since it's a theoretical astrophysics institute. And I just want to define two sort of characteristic timescales. The first is just the cooling time, which for pure Bremsstrahlung scales like temperature to the 1/2 power divided by the density. So this is just pure Bremsstrahlung down here. And the second is the free fall time. This is the time it takes for a material to fall to the center of the galaxy cluster. And these are going to be two of the most important time scales. So first of all, let's just assume there's some sort of difference between the heating, or between the cooling and the heating. And that the heating scales like some power of the density. So alpha equals 0 is constant heating per unit volume. Alpha equals 1 is constant heating per unit mass. So these are sort of the two most plausible ways that any sort of heating mechanism behaves, or mechanical work, or what have you, could actually heat the galaxy cluster. So to quote a very old result, which probably a lot of you are familiar with, this is from George Field in 1965. When the derivative of this function with the temperature is less than 0, you have local thermal instability. Basically what this means is if the temperature goes down, the cooling rate goes up faster than the heating rate goes up. It actually is pretty simple. And the thermal instability growth rate is roughly a cooling time. And so, so both heating per unit volume and heating per unit mass are actually unstable to local thermal instability. And so I'm going to argue in this talk that you have multi-phase structure when this cooling time is much shorter than this free fall time. So this is just some rough sort of time scales that I want you to keep in mind. And so I'm going to show you some simulations. And in these simulations, what we've done is we'd like to study local thermal equilibrium. But if we just turned on heating and cooling everywhere, we'd rapidly have, or if we just turned on cooling, we would just have a cooling flow. And the whole atmosphere would monolithically collapse. So we'd like to be able to study local thermal instability in the context of global thermal stability. And so what we do is we impose a global thermal equilibrium where the heating rate as a function of position is equal to the average cooling rate. And we let this evolve. And so I'm going to start by showing you some simulations, just in local Cartesian boxes, 2D or 3D. It actually doesn't make any difference between 2D or 3D for these. And what I'm plotting here is, this is going to be a movie, which is the log of the density, where gravity is pointing down, and this is a few scale heights high. And this is for two ratios, the cooling time and the free fall time. So one where the cooling time is very short, and one where the cooling time takes longer than the free fall time. And you can watch the difference that happens. So over here on the left, where the cooling time is short, you start to see that the cooling instability goes nonlinear before the blobs can fall. And so you actually start to develop multi-phase structures. It begins to rain down towards the midplane. And these grow in size until the cooling time is roughly similar to the free fall time, which I'll show you, and then freeze out. Whereas on the right-hand side, there's no extended multi-phase structure. The density contrast remains linear. But that doesn't mean that there's not anything going on. And the key parameter here that differentiates these is the cooling time over the free fall time. And you can see what dramatic differences you have between these two simulations. And I'll tell you now that in Cartesian geometry, the critical value of this is about 1. When we actually test this in spherical geometry, it's closer to 10. And that's because you get some additional compression as blocks fall towards the center.
Okay, so is there a background temperature or something? It
So
looks like you have convection going on.
So initially, I think this is initially an isothermal model. We have both isothermal and isotropic initial conditions, which give very similar answers.
And the heating rate, how are you distributing it? Is it just random?
Yeah. So in this case, it's equal to the average cooling at a given height. So I'll show later that we can relax this significantly, and it's not sensitive to it. But this enforces the global thermal equilibrium. Otherwise, the whole atmosphere would collapse and make a very boring movie. So, all right, I have to tell you what equations I'm actually solving. So in the full generality in this talk, we'll be doing 3D magnetohydrodynamics with some of the additional Braginski physics. And we're using the Athena code. And this is a nice slide with a whole bunch of unpleasant equations. But this is just the continuity, conservation of mass, conservation of momentum, conservation of energy, the induction equation. And if these are all the equations of MHD, they would actually be very easy to solve numerically. Unfortunately, there's this one, which makes it much harder to solve numerically. I won't go into the details of the numerical scheme, but I just want to mention one point that I'll return to later in the talk. And that's that the intracluster heating is in an interesting limit. It's not collisionless, it's collisional. And that the mean free path is smaller than any of the other size scales in the problem. But it's very anisotropic, and that the mean free path can be as much as 12 orders of magnitude larger than the gyro radius. We're talking gyro radii that are in thousands of kilometers. This is in the core of the cluster. So you'll see later that thermal conduction is not only important, but it's highly anisotropic. And I'll come back to this point. But after that, I just want to show you, in case you didn't believe the movies, this is sort of a rogues gallery of our simulations with multiphase structure. And this is starting with an isothermal initial condition, and you can see it doesn't matter. So this is heating per unit volume, this is heating per unit mass, and this is all the way from over on this side over here, where we have a long cooling time relative to the free fall time. So some of these plots have thermal instability instead of cooling time. Whereas here, this is characteristic of that movie you saw earlier on the left, where you have strong nonlinearities and big overdensities that start to fall. And to go back to Shane's question, so we've been enforcing this global thermal equilibrium. And you might say, well, you just put that in by hand. And we did, but it actually doesn't matter. So what we do is we take our fiducial case and then we impose perturbations to it, fluctuations both in time and space that cause the global equilibrium to go out of balance. And so this top row is the movies I've shown you before, whereas this middle row is about 100% fluctuations about heating equals cooling, with a correlation time that's equal to the cooling time. So this is roughly trying to come, this is more like what you might see in a real system, because it can actually respond on time scales faster than the cooling time. And you can tell that these two are actually pretty similar. So I would argue from this that our prescriptions are actually somewhat robust to our variations in heating and cooling. However, if we go all the way up to 300% fluctuations, we just return to the cooling flow limit. You're not able to maintain enough global thermal equilibrium to see any of this multiphase structure develop. And so let me be a little more quantitative about it. So first of all, if you focus on the plot on the left over here, what I'm plotting is the saturated RMS density fluctuations as a function of the cooling time over the free fall time. So this is the same ratio I showed you, and these stars are 3D, and this curve is a parameter study in 2D. So you can see that the 2D and 3D give you very similar results. And first of all, it's quite obvious that the amplitude is a strong function of this cooling time ratio. And what happens is, basically this just saturates at some sort of linear value once the cooling time is close to the free fall time, when the blobs become sufficiently dense, and then they cease evolving. It sort of freezes out. Whereas on the other hand, weak cooling saturates with this density enhancement being linear, and it actually turns out that it drives internal gravity waves. I don't know if any of you are familiar with the work by Balbus and Soker. This is a paper from a while back in the literature, I want to say 86, 85. And I could return to discuss where some of the literature is, because there was some confusion in the literature in the past. And these, in some sense, this is almost more interesting, in that this drives internal gravity waves, which actually drive some of the mass flux down into the galaxy cluster core. And you can see the other way to look at this is if you want to look at the cold fraction. So this is the amount of material that's passed into our cold phase from everything initially being in a hot phase. And it's very much as you would expect. When the thermal cooling time is short enough compared to the free fall time, you end up with almost all of your mass in the cold phase. Whereas in the other case, everything remains in a relatively hot phase. And you can do some analytics. I'm not going to put all this up on the board, but you'll find that this ratio of the saturated overdensity actually scales like the free fall time over the cooling time. So 1 over this ratio. So what gets a little more interesting when you start to think about what is this doing to the mass accretion rates. So in some cases, the simplest case and the least interesting one is when its cooling time is really short, where you get these really crazy filaments falling down. And in that case, what I'm plotting here is this is the mass accretion rate divided by what you would get from a cooling flow. So we've tried to normalize this to start to put this back into the context of galaxy clusters. And what you find here is when you have these big blobs, they actually carry a lot of the mass because they're so overdense, and you get almost a cooling flow's worth of mass radiating in as time goes on. Whereas in the other case, what you find is when this ratio is about 1 in the Cartesian system, 10 in the spherical system, which I'll come back to, is you get an interesting suppression of the actual mass flux. And so we're defining this as the mass flux through some sort of zone near the bottom. Sorry, through some sort of level near the bottom of our simulation domain. And you see that it's actually strongly suppressed compared with the cooling flow value. So this is 1/100th of the cooling flow value, or even 10 to the -4 of the cooling flow value. And this is starting to get interesting, because this is getting closer to the real regime where clusters can actually live. Some sort of mass actually has to be cooling and feeding the black hole, and we observe it actually. We observe some amount of iron lines fluorescing as we move further down. And you can show analytically that the mass flux divided by the cooling flow is going like this ratio squared. Okay, so let me take a little bit of an interlude, and let's try to continue to inject a little more physics into the problem. So the simulations I showed you before just had hydrodynamics, heating and cooling. Magnetic fields really didn't play any role in it. But now let's put the magnetic fields back in. And with that, the anisotropic conduction that goes along with it. And so as a result, what you find is that the field's length, so this is the length scale that thermal instability grows on in a magnetized medium. So basically on scales smaller than the field length, conduction can be fast enough. And so material starts to cool, conduction kicks in, it just evens it out, so things on smaller than the field length can actually go thermally unstable. Bigger than the field length, the conduction time is just too long. It can't keep the thermal instability from happening. But now that we're in this cluster environment, the field length is very anisotropic. Along magnetic field lines, it's whatever it is. It could be 5, 10, 20 kiloparsecs. But perpendicular to the magnetic field lines, it's nothing. It's absolutely tiny. And so this suggests that we can actually have some anisotropic collapse. And so what I'm going to show you, a simulation here, is more realistic. So it has magnetic fields and anisotropic conduction. We've also done it with cosmic rays in it. And we start with an initial magnetic field at 45-degree angle. And the colors are going to show the density in the magnetic field, which are tracking each other because the field is frozen in. And then the arrows show the direction of the magnetic field, which is kind of hard to see. And what you're finding is the overdensities are very nicely tracking the magnetic field lines, and you're getting very anisotropic collapse. And this turns out to be very computationally difficult for reasons I can go into later, if you want to ask. And what we find is the filaments are aligned with the local magnetic field. And when we include cosmic rays, they have a large non-thermal pressure, both from the cosmic rays and from the magnetic fields. There's definitely some speculation as to what's holding these magnetic filaments up in pressure balance. And there's not enough pressure in the molecular and atomic gas which is reserved for them to hold them up in the intracluster medium. And so if we introduce this physics back into the problem I was talking about earlier, with the thermal instability and these sort of cooling blobs, so where filaments are aligned with the local magnetic field. And so this is the same case. So this is the movie that was on the left-hand side, where the thermal instability time is quite a bit shorter than the free fall time. With no conduction over here, you get the same, and this is just a snapshot taken from it, with an initial magnetic field in that direction. You get the same physics, where the blobs just form and drop down. Whereas with the thermal conduction, you tend to get these sheets that form. And so real physics leads to filaments and not cold blobs, similar to what we've seen. Okay, so you may not believe me until we actually move to real physical systems. So we did a lot of work in these Cartesian boxes to really try to understand the physics and get a handle on all the analytics that was going on. But then we translated our system to an actual 3D global cluster geometry. And we do our best to build cluster models, which are initially in some sort of equilibrium. And here we find that this is where the condition has changed, where the cooling time over the free fall time is less than 10 to get multi-phase structure. And this happens because as the material starts to fall in, it gets additional compression in spherical geometry relative to Cartesian geometry. And to put this in sort of units that you might be more familiar with, if you know about clusters, this is the ratio of the cooling time with the free fall time. 30 is it's a sort of the stability boundary between cool core and non-cool core clusters and the distribution. And so what happens in this case? Well, with this more realistic feedback, Again, we find the same thing happen. So what I'm showing you here is this is the cooling rate. This case, not in solar, not normalized the cooling flow rate, but in solar masses per year versus time. And these are for various initial entropies. And so you can see for an incredibly low initial entropy, which I'll show you later is never actually observed, the mass flow rates are ridiculous. This is basically a classical cooling flow. Whereas in other cases, where we're in the regime where clusters are actually observed, sort of 10 keV centimeters squared, you find these very episodic bursts, where you get a burst of cold material falling in, and then the system comes to thermal equilibrium, and then you get another burst of material falling in. And if you move to a cluster with a very high central entropies, these are your non-cool core clusters, where the cooling time is quite long, you find that there's very little mass accretion. And again, we see this same suppression factor. And in this case, what we've done is we've moved away from this prescription of sort of manually enforcing this global thermal equilibrium. And we've moved to a model where we actually track the material that falls down into the center of our galaxy cluster. And our imaginary black hole at the center drives heating that's proportional to epsilon m dot c squared, so some sort of fraction of the energy that you can extract from it. And what we find is that clusters start to self-regulate themselves. Their entropy profiles start to saturate at a value where the minimum cooling time over the freefall time is somewhere around 10, which corresponds to entropies in this 10 to 30 keV centimeters squared regime. And let me show you an example, just so this is a little bit more clear. So this is one of our fiducial models. This is a few times 10 to the 14 solar mass cluster. So this is right in sort of the middle of the range of a garden variety galaxy cluster. And this is our initial profile, the solid black line. And this is an entropy. So there's a big entropy core. This is characteristic with what's observed, followed by a power law out to large radii. And this is the same cluster, but plotted as the ratio. This is the cooling time to the freefall time. That might be hard to see. You get a sense this ratio shows up in a lot of our plots. And what you find here is that the system evolves, actually. The entropy is able to bounce around a little bit. Cold material is able to fall out and actually trigger the feedback, which then heats the cluster back up. But we haven't entirely solved the cooling flow problem, because I think the epsilons that we're finding are a little bit too high. So, but we're making some progress towards understanding how these systems can self-regulate.
You need to say you're putting in different epsilons, or?
So we've tried different epsilons.
And the epsilon you need to get it to work out.
Yeah, this is closer to like 10 to the minus 3, which I think is probably a little too high in the m dot c squared. I think you probably would want something a little bit smaller for a real system. I don't think black hole feedback is quite that efficient in terms of actually shooting jets out and coupling to the intercluster medium. In this case, so each simulation has a fixed efficiency for feedback. And this is actually true over a range of scales. So this is true for both cluster scales. So this is one fiducial model for a cluster. This is where we change the feedback parameter in red. Sorry if anyone's colorblind. And then in green, this is actually group scales. And,
so it's fine.
Yeah, so, and in group scales, actually, the feedback ratios we find have to even increase a little bit more. So groups are a really tough place to solve the cooling flow problem, which no one really talks about. And it actually turns out it's pretty only weakly dependent on the feedback model. But one thing I want to emphasize is this is all intrinsically multi-dimensional physics. You don't get any of this thermal instability and self-regulation in 1D. You need at least 2D, and preferably 3D, to have these cold blobs condense and move past the hot intercluster medium and trigger this feedback.
Sorry, I think I missed it. How do you distribute the energy?
Yeah, well, you're going to miss it. I didn't tell you. So. Right, so we've just adopted a profile, which is fairly peaked towards the center.
Okay.
So I'll mention later that we're not doing anything real. So we've chosen a spherically symmetric, azimuthally symmetric profile to distribute the energy. That's the hard problem, by the way. So, Yeah, no one's solved that part yet.
Yeah, but that value of 10 comes from picking a particular epsilon, or do you get that independent of epsilon? The addition.
That's actually independent of epsilon. So provided it's in some sort of reasonable range, doesn't pull too much, doesn't too high. And when we try to put this in context of the observations again, in terms of what we're going to argue is the self-regulation of halo. So what I've plotted here, this is some nice results from Ken Calvignola and Mark Boyd. And this is the number of clusters as a function of central cooling time. This maps very well to the entropy distribution. And you can see these are your typical cool core clusters, and here are your non-cool core clusters. And you notice that there's no clusters with a cooling time shorter than what about the typical free fall times in the system. So this is one of the reasons we argue that there's clusters just don't live down in this regime where the cooling times are shorter than the free fall time. And they typically peak right in the value where it's sort of around 5 to 10. Sorry, this should be T free fall. And so this is consistent. I'm not going to claim this is, we've proven this, but it's consistent with mass fluxes that are induced by thermal instability. And to further compare with the observations, so we've taken the accept catalog, which is a nice database of all the clusters in the Chandra archive. And we've matched it with these very nice samples from Mike McDonald from Maryland, who's gone out and looked for whether there's H-alpha filaments in all of these clusters. And so we've taken this set of clusters, and what we've done is we've plotted the cooling time versus the free fall time, and we've constructed the masses for all of them. And we've color-coded these according to whether there's no extended H-alpha or there's extended H-alpha. And you can see that these curves start to look like they're going to separate. And if I plot this perhaps a little more suggestively, where we've now gone to this curve and we've measured the minimum of this ratio, the cooling time to the free fall time, and plotted this versus the cooling time, you'll find that these systems start to separate. And it suggests filaments start to occur at this critical value of around 10. And so we thought this was pretty neat that the observational results sort of were pretty well in correspondence with our simulation. And in particular, this minimum is occurring somewhere around 10 to 30 kiloparsecs, which is exactly where the filaments are actually found in the clusters that have them. So I want to say that things are sort of starting to hang together. And I want to give you a sense of where we're going to go with this. So one of the neat things we've done is we've worked very hard to get a static mesh refinement version of the code up and running that includes all of the various physics. And what I'm showing you here is this is sort of a mock cluster where we've zoomed in continuously. And what we'd really like to do, and I think we've managed to make things just efficient enough to do that, is that we can resolve scales all the way from the cooling radius of the galaxy cluster down to the black hole sphere of influence. And you can see what happens is, out here there's nothing going on. It doesn't know that there's any cooling going on at the center. But as you get close to the center, you see these blobs start to fall in, and some of them actually carry quite a lot of momentum, and then they're all subsonic. But you can see that this is a Mach number, and this is 1.1. And I just thought it's pretty neat to have 4 orders of magnitude and radius resolved here in these simulations. And so this is going to allow us to answer some of these questions of, is it hot versus cold accretion taking place at the center? What's actually feeding the black hole? And we can also try to look at jets and see what these things really do in actual systems. Okay. So good. I think I'm pretty well on time. And I'd like to move from the inside to the outside. I can either let you take some questions. Any pressing questions now before I move outside the cooling part?
So the main result is that you have this fairly particular cooling to free fall time that you pick up, and that's not sensitive to that sensitive to the efficiency of the feedback and the profile of the feedback. That's just because there's such a strong dependence of the instability mass accretion rate of this.
Yeah, that's what's really driving. So basically it's the sensitivity to how much mass is actually condensing out and feeding our feedback mechanism. That's really what it drives. Of course, if you choose an epsilon that's either way too efficient, you'll blow everything out, or way too low, you'll actually...
Did you try playing around with how you put in heating?
Yeah, we tried playing around with it. Actually, it turned out that, I mean, this is a really interesting problem that we're working on. And the feedback needs to be fairly centrally concentrated. You need the feedback, you need the heating to be happening where the cooling is happening.
You mean by in what scale?
So you want it sort of around 20 kiloparsecs. That's kind of where you want it to peak. And this is where you really have a lot of the cooling times become very short. This is a very tricky problem. How do you actually solve that? And one of the things we're actively working on. So you are correct, and it's somewhat sensitive to how you do the feedback. Maybe even slightly uncomfortably so. But in the regimes where the feedback is working, then we find it's insensitive. Okay, let me turn to the outside of galaxy clusters. So I'm going to step outside of, so before I was talking basically about everything to the left of there. And now there's a whole other world outside of here. And what I'm showing right now is there's a Japanese satellite, Suzaku, that launched a couple of years ago. And Suzaku has the advantage of being in a low Earth orbit. It's not way out there where Chandra is. And so it's somewhat shielded from all of the particle background. So it has the advantage that it's able to look at, it doesn't have the same problems with charge exchange that Chandra has. So it's able to look at much dimmer objects, lower surface brightness, which means the outskirts of galaxy clusters are now accessible for the first time without using millions of seconds of Chandra time. And so these are some very nice results from Matt George, where if you just focus on the solid black line here. This is for Parks 0745, which is the first cluster where they actually went to the virial radius and beyond to measure a characteristic temperature profile. And you can see that these temperature profiles are declining in radius. And this is a very generic fact, that they tend to decline with radius steeper than what an NFW profile would decline with radius, which is the dotted line. And so this has been known generically true within the virial radius, but it's nice to see that it goes even further out. And so let me remind you just a little bit about hydrodynamic convection. I'm sure most of you are already familiar with this from your courses on stellar structure. But hydrodynamic convection has been known about for a long time, and you would characterize it in terms of the Schwarzschild criterion, which is a condition on entropy. And the motions are slow and they're subsonic. And basically the way to think about this is if you have a gravitational field pointing down, there's a high entropy down here and low entropy up here, and you take a blob at some initial density and pressure and entropy, and it moves higher, as it comes to a new pressure equilibrium in the background fluid. Essentially what happens, if this entropy gradient is negative, then the final density is less than the background density when the blob is buoyant and starts to rise. If this entropy gradient is positive, the other way is true. And it just sinks back down to where it came from, and then this is what we call internal gravity waves. They're just the Brunk oscillations. And so the criterion for traditional convection is a criterion of entropy is the source of free energy. So now let me explain the magnetothermal instability, or MTI. And we're back in this, it becomes important again that the heat fluxes are anisotropic. And so they're given by this conductivity that's only along the magnetic field lines. And so classically, let's just start with an atmosphere that satisfies the Schwarzschild criterion. So gravity is pointing down, the temperature gradient is also pointing down. So it's hot on bottom, it's cold on top, and it's classically stable according to the Schwarzschild criterion. But now in this long mean-free path, we have another criterion. And basically, the way this occurs is that imagine I take a blob of fluid right here, and I raise it up to a height just a little bit higher in the atmosphere. As I pull it up, it adiabatically expands as it comes to pressure equilibrium at its new height, which means it's cooled just a little bit. But it's connected by this magnetic field winder reaching deeper in the plasma. And these magnetic field lines are perfect conductors. So heat begins to flow along the magnetic field line. This starts to heat up. It becomes buoyant. It starts to rise. As an ideal MHD, which is a good approximation for galaxy clusters, the fields are frozen in with the fluid. As it starts to rise, the field becomes more aligned with the background temperature gradient. And you can see how you have a recipe for a runaway instability. So now, we're actually able to tap into the temperature gradient as a source of free energy. It almost seems like voodoo, doesn't it? But to show you it's not voodoo, I'll show you a movie. And so this is just a very simple simulation from that exact same snapshot I just showed you. And it's basically gone rapidly unstable and completely reoriented the magnetic field lines. And so you might think the way that this instability saturates is by taking these horizontal field lines and making them completely vertical. However, that's not actually what happens. In this case, it just exhausted the source of free energy. We just let the temperature gradient go to zero. And that's one way it can saturate. But in real systems, that probably doesn't happen. So instead, what happens, if you imagine now that we keep the temperature fixed, so again, we're working in Cartesian boxes just to try to understand the physics of what's going on. So we fix a hot temperature at the bottom and a cold temperature at the top. It turns out that the instability does not actually saturate quiescently. It actually saturates with very vigorous convection, continuing to tap this temperature gradient. And to understand it, let me show you this. So imagine we start with vertical magnetic fields. So linearly, this is stable to the MTI. I can't take any parcel of fluid and move it up or down and tap into the temperature gradient. However, imagine a zero frequency mode where there's just some sort of displacement. What you can see now is basically any sort of horizontal motions will drag the magnetic field lines with them, which reestablish this horizontal magnetic field. These horizontal displacements experience no restoring force from the buoyancy, and they're completely not damped. And so what happens is this can reseed the instability. It's non-linearly unstable because it's not linearly unstable, it's non-linearly unstable. And this reseeds the instability, which closes the dynamo loop. And you can see that in this simulation, it starts to result in very vigorous convection again. So this instability does not saturate with vertical magnetic fields or radiomagnetic fields in the context of a cluster. There may be a very small isotropic bias. It generates vigorous turbulence, which in some of the cluster simulations I'll show you can actually be supersonic. And if you give it enough time, the magnetic dynamo is very slow, but given enough time, it can amplify the magnetic field all the way up to equipartition. Now what's interesting is another source of turbulence does not suppress this instability. So let's try to build a cluster model to study this. So I'm going to show you 3D MHD simulations of a cluster that sort of resembles Able 1576. So this is a fairly hot cluster. And what we're going to do is we're going to fix the temperature gradients here and here, at the inside and the outside of the galaxy cluster in our simulations. And we do this because basically every galaxy cluster that's been observed seems to have some sort of cosmological process that's setting this fixed temperature gradient. Actually, that's something one of our other projects I'm not going to talk about today, is what sets this temperature gradient that seems to always exist in the outskirts of galaxy clusters. And since we're doing this non-cosmologically, we're just going to impose this boundary condition. And there's no cooling. Cooling's not important outside of a few hundred kiloparsecs in galaxy clusters. We start with an initially tangled magnetic field, and in this case, the instability e-folding time is about 600 million years. And so this is one of the snapshots. This is sort of a 2D slice through a simulation. What's going on? Yeah, there's not enough. These files are really big, so actually I need to make a better movie at this one. But you actually end up with fairly vigorous convection. Now, if we look at this a little more quantitatively, what I'm plotting here is I'm plotting the RMS Mach number. So the velocity divided by the sound speed, and the galaxy clusters versus position. And so for this cluster R500, where the density is 500 times the critical density, is about a megaparsec. And the real radius is about 1.6 megaparsecs for this cluster. And so what I'm showing you is the blue line here. This is a simulation with just the MTI only. And you can see that you're getting up to somewhat interesting values. Mach number is 0.2, 0.25. This doesn't provide a lot of pressure support, but it provides a little bit of pressure support. Although the maximum Mach number, not the RMS Mach number, is actually already supersonic. What's interesting is there's other processes of turbulence that's going on. Structure formations happening all the time. Galaxies are falling in, bigger structures are falling in, and these drive their own sort of turbulence. And so this is something that Christoph Kromer had worked on a little bit when he was here. And if we model this by driving turbulence in addition to the MTI turbulence, you find that these actually add together. So this red curve is just some driven turbulence that we put in by hand and drive in an uncorrelated fashion on a range of scales. And instead of suppressing the MTI, these two just actually add up to result in a plot curve. So they add linearly in energy, which means they add in quadrature in the Mach number. And this saturates fairly quickly. And the other thing you might want to know is, well, could this introduce a bias in the amount of non-thermal pressure support we have? So we've taken a model cluster and we're looking at different temperature drops in the outskirts of the cluster, all the way from 3.5 kV to 5.5 kV. So similar to the ranges you might find over moderately hot clusters. And you can find that there's a difference in the saturated velocities, just scaling like the temperature gradient to 1/2. And this is consistent with mixing theory. So again, if you go back to this fact that I mentioned that we're interested in clusters for cosmology, what you'd like to know is you'd like to know the total mass. And so if you have any sort of non-thermal pressure support, you can see how this starts to become a problem when you're trying to measure the total masses of these clusters. And so if we even go to a bigger box, which goes beyond the virial radius, we find that these turbulent values are just increasing all the way to the outside. And so now instead of Mach number, I'm showing you the turbulent pressure support divided by the thermal pressure support. And it's already up over 30% in the outskirts of galaxy clusters. And so you can see that this could have some sort of significant effect on the measurements you make that measure the hot intercluster medium near the cluster outskirts. Okay, so I'm going to start towards wrapping up and try to connect this to observations and tell you why you should care about this and other sources of turbulent pressure support. So probably all of you are quite familiar with the Sunyaev-Zel'dovich effect, but I'll go through it very quickly just in case someone hasn't seen it. I know there's people here that work on it. So it's essentially inverse Compton scattering of the cosmic microwave background off the hot electrons in the galaxy cluster, and it produces a pure spectral distortion. There's a characteristic frequency of 218 gigahertz, which is the Sunyaev-Zel'dovich null. And then experiments that have been designed to measure this often have detectors of 150 gigahertz, and some of them have detectors of 220 for the null. Some of them have detectors over here to get the increment, the decrement. And you can, and by the way, this figure is incredibly exaggerated. It's actually a pretty small signal. But the nice thing about it is, unlike X-rays, when you're trying to measure galaxy clusters, it's pretty redshift independent. And this comes from the fact that the angular diameter distance is fairly flat and high redshift. And the signal is just proportional to the total thermal pressure. And so you'll often hear this called the Compton Y parameter. And so one thing you can do if you want to try to do cosmology with the SC effect is you can take this and you can measure these total Compton Ys for various galaxy clusters. And you can try to calibrate a YSC mass relation. They've also done this for the X-ray, where they've come up with an X-ray version of this. And from this, you make all these measurements of galaxy clusters. You get their Compton Ys, which give you their masses. And then you get a mass function. From the mass function, you can sort of derive properties like the magnet sigma 8. This has been generally successful. The other way to go at it is through these big SC surveys, which are basically all sky, looking at all the nodes of the CMB. And so this is the entire microwave sky, and this is basically one of these coefficients, L times L plus 1, blah, blah, blah. And this is the function of L, so the scale on the angular scale on the sky, in terms of the mode number. And so this is your typical CMB here. But then you see way down here is the signal from the thermals and the Sunyaev-Zel'dovich effect. There's additional signals called the kinetic Sunyaev-Zel'dovich effect, which I'm not going to talk about. And then there's some noise here from Poisson point sources. And there's a lot of galaxies that can get in the way, flat spectrum IR sources that contaminate this process. But sigma 8 ends up just being incredibly sensitive on the value of the Sunyaev-Zel'dovich effect. Say, for example, at L of 3000, which is what a lot of the people do. So these are the results from SPT. I know there's people here involved in the ACT project. I just happened to grab this one. I have split loyalties on the ACT SPT. Having been at both Princeton and Berkeley, so I want to try to pigeonhole me. And the first results, so basically what they've done is they have to have some sort of template for what the Sunyaev-Zel'dovich effect looks like from all these galaxy clusters. And the first results gave a value for sigma 8 that was actually a bit low in statistically significant tension with other probes. So with the sigma 8 that we like to think we know. And so this meant that there was something wrong. And so the SE template basically was over-predicting the amplitude. How much SE signal you would get for a given galaxy cluster. So one thing, the group here, led by Nick Battaglia, who just graduated, and company, they pursued this in terms of AGN feedback. And so they took their cosmological simulations and they turned up the AGN feedback they've been running. And so these two different grade curves are the ACT and the SPT constraints. And then this red line here is the one you should pay attention to, which his simulations rerun with an increased value of AGN feedback. The other thing that you can do this is turbulent pressure support. You're pushing material out. The non-thermal pressures supplanting actual X-ray emitting or Sunyaev-Zel'dovich signal producing material. So this is the other way that you could actually explain some of this under-prediction of sigma 8. And so this has to be studied more in actual cosmological simulations. And one of the worst problems with it is much of the signal is actually from group scale objects at intermediate redshift, which we just don't know a whole lot about. And so I'll summarize by saying that's a hard problem, and more careful simulations are actually needed. So there's a lot to do in this area. Okay, so my time is running short, so I'm just going to summarize. And so you've probably heard me say the ratio of the cooling time to the free fall time 30 times in this talk. So if you take nothing else away from it, I want you to remember that galaxy clusters are globally thermally stable. There's no cooling flows, but they can be locally thermally unstable. And it's this ratio, the cooling time over the free fall time, that sets this behavior of local thermal instability. And if it's short, we find multiphase structure. And this is pretty consistent with the observations as I've shown you. And a reasonable heating model, so this epsilon n dot c squared formulation, can actually reduce the mass fluxes that cool down to read values that are consistent with those that are observed. And this sort of behaves, this can behave in a self-regulatory cycle, whereas clusters become, the cores become too cool, the cooling time becomes shorter, mass condenses out, it feeds the black hole feeds things up, and this is a very plausible feedback cycle. On the outside of galaxy clusters, if you're trying to do cosmology with the Sunyaev-Zel'dovich effect, the MTI could produce significant non-thermal pressure support, in addition to that from structure formation, which it adds to. And so this is another way of explaining some of these discrepancies with the measurement of sigma 8. And I'm just going to end with a few open questions, but I don't want to pretend that we've solved everything. So one is one of the questions we're trying to get at right now with these simulations. Let's just people talk about cold and hot galaxy accretion is the accretion under the black hole, hot or cold. Are you cold blobs actually feeding it? And then this is the problem that several of you asked about, is how does all this energy actually couple to the intercluster medium in terms of jets, bubbles, shocks, sound waves? And the only way you can get at this is numerical simulations and careful comparisons with the observations. There's some question of how do you constrain these models of multiphase structure and cooling, and the new Astro H could help a little bit with its high resolution X-ray calorimeter. And then this is the heretical question. There really is a lot of this non-thermal pressure support. Are we really ever justified in playing this game where we go from observable, either X-ray or Sunyaev-Zel'dovich to a hydrostatic mass, to a total mass that we then use to constrain cosmology? Will cluster cosmology ever really be competitive with our other forms of cosmology? So that's heretical. So you can cut that out of the recording. Anyways, thank you for your attention.
We have time for questions. So I had a question. So for the MTI, is there, I mean, comparing to sort of get at what, this turbulence from other sources or other pressure support, is there any way to get another handle on how much of that is through the MTI? And I guess if you have observations of magnetic fields, you guys said there's this dynamo happening there. Do you expect that to give you a handle on that? Or?
Unfortunately, observations of magnetic field are very tough in galaxies.
No, I know, but is it impossible, or is it?
I think it's next to impossible, to be quite honest. So Christoph had a paper where he was able to infer the magnetic field in a few places in Virgo.
Yeah.
It is consistent with the MTI acting. It's also consistent with radio windfall driving the magnetic field lines out. These are questions that should be answered a little bit more in some cosmological simulations we're trying to do with collaborators. But it's pretty hard to get at it that way. There will be X-ray calorimeters coming online that can directly measure the amount of turbulence, but I don't know that they'll be able to do that in the outskirts.
So the asteroid age.
Asteroid age.
It's going to measure the line list. And
Third time's the charm. So the first one blew up, the second one had the calorimeter short. So it works this time.